Hello, everyone. This is Sadhana Alangar, HL7's Director of Education. Welcome to DevDays and to this presentation on synchronizing systems using whole system history by Arnold. Robin, if you're ready, take it away from here.
Yes, thank you. So hello, everyone. I am Robin Arnold. I'm the performance engineering lead at Watson Health for the IBM FHIR Server. I also lead the development of the FHIR Server persistence layer, focusing, on the ingestion code, the JDBC, insert statements, and all that kind of stuff, and also all of the query building that we do for FHIR Search and so on. So we have the IBM FHIR Server is an open source project that's hosted at GitHub. You'll see the link there. And we've actually just merged into our main branch, the R4B version. So we now support both R4 and R4B, although R4B has not yet been released yet. We don't have a release. So as part of this talk, what I'm going to do is talk about how we can use the whole system history interaction, and particularly how we can use that for synchronizing systems. So that'll be involving some discussion about the REST API, the sort order limitation that we have with R4 currently, and some discussion about how we can actually get around that, and also discussion on some consistency issues that you'll face when you're doing this kind of thing. Then towards the end, we'll talk about optimizations for increasing throughput, and some deployment considerations as well for scalability, for when you have a lot of data flowing through the system. So the history interaction, there's a small line in the spec that says the history interaction can be used to set up a subscription from one system to another so that resources are synchronized between them. It's a bit of a throwaway line that's just kind of snuck in there, but we thought it would be interesting to actually take a look at this and see what it would actually mean to use this in the real world. And we've done an implementation which I'll come on to in a second to basically demonstrate the capability. So what does this synchronization really mean? Well, it means that you would introduce some kind of component, the sync component box in the middle here, and it's going to poll an upstream FHIR server, calling the history endpoint, get the bundle data back, and then basically push that data down to some downstream system, which could be another FHIR server, or it could be some other queue system like Kafka or whatever. So what does this history interaction look like? Well, if you're not familiar, so there are three variants. There's instance level, where you can get the history of resources, basically the resource history for a single logical resource. So version 1, version 2, version 3, and so on. Then there's the top level, which is basically the type specific history. So that would be, say, show me all of the patient data, maybe, or all of the observations that have been ingested into a particular system. And then there's the whole system, which goes across all of the resource types. And this kind of represents almost like a change log. So all of the different kind of resources that have been put into the system, including logical deletes as well. You get basically a bundle back that shows all of these. So on the right-hand side here, we've got the response to the history call, to the whole system history call. And as you see, it's a history bundle. And there's an entry array where each element in the array is basically a collection of some metadata related to the change, the request, basically, how was it? Was it a post or a put, or was it a delete? And then the response that the server would have given. So that includes the full URL. Some last modified time, and then also at the top there you see the link. Basically, this is related to the pagination. So you're obviously not going to get the entire history of the server all back in one call. So you're going to want to page through, multiple times there, following those next links. So Another part of the FHIR R4 spec says this. This is the return content is a bundle with type set to history containing the specific version history, and the most important piece, sorted with oldest versions last. Now, when we saw this, or when we started implementing it, it was like, hold on a minute, there's an issue here. So oldest versions last, that's very reasonable as a response for, say, human consumption, because it means that I'm going to see the most recent, the most up-to-date data in the first page. But for system synchronization, that presents a bit of a challenge. For system synchronization, you need the changes to kind of be replayed in order, in the order that they arrived, kind of like a first in, first out process. So this is an issue here. So how do we get around this? Well, with R4, unfortunately, there's not really any way to get around it as far as the spec is concerned. So what we did is we raised the issue in Jira, and we had a chat on Zulip with some of the stakeholders, and basically agreed with this kind of proposal. So the idea is that the client can now pass in a sort parameter, and you have 3 options. So if the sort is none, then the ordering is system defined. And we can leverage that, or a system can leverage that if they've got a certain kind of way of ordering resources. You can either have then ascending or descending sorting based on the last updated timestamp. And so the default there is the current behavior, which is the R4 behavior, which is sorting basically by descending timestamp for last updated. So we've actually implemented this already in our IBM FHIR Server 4.11 release. If you're interested in going out to GitHub and taking a look at that. Just want to talk a little bit about consistency here. So one of the issues when you are kind of trying to synchronize data between 2 systems is those systems getting out of sync, and that can happen very, very easily. So I've got a couple of scenarios here. Let's say we've got a very simple system where we're maybe updating a row in the database, so maybe a new version of a resource or a new resource comes in. So in scenario 1, we decide to send out a notification to say that the resource has arrived, and then maybe the app server crashes before the transaction gets committed. So now we've already sent the notification, but the resource didn't get stored in the database. Scenario 2, when we were coding it, maybe we decided that we wanted to issue the notification after the commit. Well, what happens now if the application server crashes before we send the notification? Well, now we've lost that altogether, right? So a downstream system that's relying on this would not actually see that change. So that represents a problem. So in a simplified way, scenario 1 is probably the simpler to do. And the way you can get around maybe crashes here would be for the receiving system to come back to the FHIR server or the source server, the upstream server, and just verify that the resource is available, is there, and is the version that's expected. Anyway, so these 2 really simple scenarios, they kind of gives you an idea about why sometimes pulling changes from an upstream server using, say, something like the history is a pragmatic solution to synchronization, and works quite well. So what might this look like in an implementation? So what you would have here is a history scanner component deployed into your environment, and this would make calls to the upstream server, the upstream FHIR server, and then basically take the bundle responses and then just push them down, maybe individually to a downstream system, which again, could be a FHIR server or it could be some other server. Now the challenge here is that this is a very sequential process. So you do the fetch, and then the upstream FHIR server is then going to have to basically read all of those resources to include them in the bundle that it responds with. Now that can take quite some time. If you've got a large bundle, it's going to have to go and pull all of those payloads together, It's going to have to do all the processing, all the serialization and everything to get that result back to you as a response. And those basically end up being random reads. They are processed usually serially, and as many people know, when you've got random reads done serially, it can actually, it can extend your response time, and so this is going to harm your throughput. Before we go on to some solutions, let me just mention checkpointing here as well. So the idea of a checkpoint is that, if the history scanner has to stop at some point, maybe there is some kind of, cloud event, if you're running in Kubernetes or something like that, the pod may be moved or the service restarted or something. And so you need some mechanism to be able to kind of continue processing from where you left off. So here, the checkpoint is really just kind of a logical mechanism that would write out some kind of ID or whatever to say that, if I restart, then I'm going to restart from this point in time. Now, one way to do that would actually be to post that as a bundle, as a resource, maybe a basic resource with some extensions to the downstream FHIR server, and then you could use maybe a transaction bundle or something to make that all consistent. Okay. So anyway, I was going to talk about an alternative approach, which would allow basically parallel processing when we go to fetch the resources. And this would allow for much greater throughput. So we know that the serial processing of requests is inefficient. It doesn't usually make the most of the available system resources. Because typically, if we're talking about cloud systems, the underlying infrastructure, probably has, hundreds of disks or thousands of disks and many nodes and things like that. So you want to be able to spread your load over all of those resources. So what if we could actually request the history, but without actually asking for the resources? So what this allows us to do, certainly in our implementation, and this is obviously, kind of implementation specific, but it allows us to do a scan of an index, which is very, very efficient. So basically, in just a few logical reads, we can pull back all of the data, all of the metadata related to the changes for a particular period of time. So between, kind of point A and point B in time. But we don't have to read the resources. Now, it does require a little bit more sophisticated checkpointing. But what this does do is it allows us to do this really efficient sequential scan, and the result is compact. So we get a lot of data back in a small amount of time. So what does this look like in our implementation? Well, what we decided to do is just basically add this prefer header, or some action based on this prefer header. So if you say prefer return equals minimal, then we basically kind of short circuit the fetches of the individual resources. And so we return a bundle where we just pass in the response the location of the resource with basically the full URL, including the version number. So basically the history with the version there. And what that allows us to do then, or allows the downstream system to do, is then go and request that resource, which it can do in parallel if it wants to, if it's got that kind of sophisticated level of processing. And then the client is basically just then responsible for following the next link that you see there, and then that's going to return the next set of data for the next period in time. So what might this look like in practice? Well, so here we've got a slightly more sophisticated history scanner where we again do the same upstream call to the history API, but passing this time the prefer return equals minimal header. So we fetch the data using the sequential scan just of this index, get the metadata back, and then we throw the requests for the individual, they're basically V reads, version reads, into a reader pool. Those are async operations. So we basically make the requests, and then we pass what are called futures. So basically these are requests that have yet to be resolved, down to a partitioner. which then feeds that into a thread pool, basically where each worker has a queue of resources to be processed. And then that processing basically involves sending the resource down to the downstream system once the resource has been read. Right? So this is a beautifully kind of asynchronous model. Makes use of multiple threads on the available platform, and also makes use of a lot of these RDBMS resources. Makes use of a large cluster of FHIR servers, maybe both in the upstream and the downstream systems. It does require slightly more sophisticated checkpoint tracking, and I've got a slide on that a little bit later. I'm just going to check my progress for time. I think we're okay. We're about halfway through. So this has been implemented as an experimental feature of the IBM FHIR server. So if you go to the GitHub repository and look at the Fireflow project, you'll see that there is a README there, and there's a CLI jar that you can run, and with just a small amount of configuration for your upstream and your downstream systems, you can use this to replicate FHIR data between two servers or two tenants of a server, or however you want to do it. So this is basically just a quick example here showing, we call a fetch, and then we basically enqueue this vread, and then the pool is actually running the vread. And then once we've got the data back for this claim, we issue a creator update on the downstream system, and so on. And so this is just a quick example. Now, I should point out, if you've seen any kind of resources in the system, my laptop here goes nowhere near any PHI. So all of the resources you see are all based on synthesized data, as are all of these IDs. Okay. So just going back to the previous slide, sorry, I should point out that, that there's an additional argument here in the fetch where we say exclude transaction timeout window equals true. This is a concurrency, not say workaround, but a concurrency issue that we have to deal with, or that everyone has to deal with, in terms of how clusters of systems work. And this is relevant for whether you're doing sort ordered by ID or ordered by timestamp. You have to be aware that in a cluster system, not all of the servers may be perfectly synchronized in terms of time, or the sequence numbers that get generated may not actually become visible in the order that you expect. So if you're using this for checkpoint tracking, you do need to be very careful about what order you process resources in. And here's a little example here that I just want to go through just to kind of explain some of the complexity around this. So here we've got 3 transactions. So think of this as maybe resources coming into the FHIR server. And so we have these kind of notional change IDs 4, 5, 7, 8, and 9. Well, these change IDs 4 and 5, they may be kind of allocated first, right? But let's say that there's some additional other processing that goes on and the transaction doesn't actually get committed straight away. But transaction 2 comes in, it gets allocated ID number 7, but it gets committed earlier, right? This can absolutely happen in a concurrent system. So now you have ID 7 that's basically visible. Think of the database in terms of ACID, so the isolation. So after the transaction gets committed, now ID 7 becomes visible, but at time 2, when transaction 1 gets committed, now we have 4, 5 also now visible. So you've got 4, 5, and 7, and then finally transaction 3 gets committed. Then you have all of those resources committed. So depending on when you look at the database, if you look at it before T2, you may think that the most recent change is ID number 7, right? Which means then that if you ask for say, okay, I've got ID number 7, let me only process data that's beyond ID number 7 in the future. When transaction 2 commits, you've now missed out on 4 and 5, right? So it's important that that you take this into account when you are doing this kind of processing, to make sure that when you make these requests, when you're doing the checkpoint tracking, that you allow for this kind of extended transaction window where data may kind of appear out of order just based on how sequences get allocated and so on. And similarly, the same is true also for timestamps, because servers in clusters suffer from clock drifts, particularly when, say, virtual machines are being moved and things like that. You can get kind of jumps in time and things like that, which can upset certain systems. And one way around this, or one kind of mitigation, is to basically delay processing of any data that falls within what your transaction timeout window typically is. So let's say it's 2 minutes, right? So what you can do is you can say, don't ask for any data that is that's younger than 2 minutes. Basically, let the system kind of settle down. So just another point here about ordering. Now, the partition, actually, let me just go back one thing I missed. The partition strategy here is very important, right? So the strategy that is suitable here. So okay, let me rephrase this. So we want to spread the load out over multiple threads. So basically, we have multiple worker queues. So we don't have like a single stream of data going to a downstream system. But there's also ordering that's important in some respects, and that is that for a single resource, you want to make sure that the versions get applied in the correct order. So in other words, you don't want to post version 2 of a resource before you've posted version 1 of a resource. So you can do this quite easily just by partitioning the data based on the resource type and logical ID. So the resource type logical ID tuple is unique according to the FHIR spec, and so that basically you just need some kind of function based on that that then would allow you to select a particular partition to process or particular worker node in this case, to process your data. And then because the worker is processing data serially, then you can guarantee that you're going to get your version 1 of the resource before you get version 2. So dependencies between resources. Well, so this can be an issue again, because we're separating out and trying to process as much of the data in parallel as possible. Well, the solution here is basically just a retry mechanism. So if the downstream FHIR server requires that a given resource is available, or a reference resource is available, then you would just have to do the retry, and it's obviously going to slow down processing on that one particular thread through that one particular worker, but hopefully the change wouldn't be too far behind. Right, so let's think about scaling out a little bit. So previously, the previous slide that you saw, that's kind of the implementation that we have, just as a proof of concept, experimental in the Fireflow project. But for really scaling this out, we could consider actually maybe using Kafka as a downstream component. So again, the upstream selection of data is the same. We'd be passing the data down to a partitioner. Again, this would be based on Kafka's partitioning mechanism, but would be using the same strategy, based on the resource type and logical ID. And then Kafka would just become that kind of worker queue. And then on the downstream system, you'd have a consumer that would be reading off a Kafka partition, and then going out to fetch the resource. So the data that we're actually pushing out to Kafka here is not the full resource, remember. It is just the metadata, basically the kind of pointer to the resource, the URL. And then the consumer could maybe pull off a kind of a batch of these messages, compose a bundle request, post that to the FHIR server upstream, collect all the data, and then push everything down to the downstream FHIR server. And then the completion messages go back onto some completion topic. Those will then get consumed by the checkpoint tracker, and then we'd be just writing out checkpoints there as needed. Now, it's an important point to note about what the messages that we put onto Kafka in this respect. So, Kafka, as you probably know, has configurable message size limits. Now, I'm sure we've all come across FHIR resources that are pretty large, like, easily in excess of 1 megabyte. And although you can configure Kafka to support large messages, this can become a problem, and it's not an arbitrary thing. You can't say really to make it kind of allow 10 megabytes, 100 megabytes, or whatever. There are limitations, and you do actually start to expose some other kind of platform level issues, like when you do start storing larger resources. With Kafka, you could potentially, have split writes, that kind of thing, causing stability issues. So my preference in this case is always to store, small, or to send small messages, and then basically use the platform to basically, pull the large resource from the server when it's needed. So this makes it much more efficient to use Kafka in this example. And you avoid those kind of large message headaches that you sometimes get there. So just to wrap up, I've posted here just a link to some of the resources that hopefully you may find useful. So we've got Fireflow, which is the project that I mentioned, that's out on GitHub. Our schema design, I didn't really talk about that much, but that is documented there. There's also an example project that's currently in feature development. It's not part of our mainline branch at the moment, but there's a class there, the FHIR Remote Index Kafka Service, for any of those of you who are interested in how you can send out to Kafka with an asynchronous pattern. So basically not waiting for the response immediately. There's an example there that may prove useful, and of course then the FHIR history link there as well, and some useful discussion about the endpoint in the spec. So just in summary then, what did we learn? The capabilities of the whole system history interaction, and how it can be used as an endpoint for system synchronization, at least certainly in the future, once the FHIR servers, maybe with R5, support that particular feature. So we discussed the API changes that we've had to make to actually support this, and some optimizations that we found useful to actually improve the throughput and scalability. So contact-wise, so I can be reached via the Hoover app in the speakers gallery. My email, robin.arnold@ibm.com. So I'm on LinkedIn as well. But the best place really to contact us, me or the FHIR team, would be through the Zoomlet chat, which is that link there. And also, if you are interested and go to GitHub and take a look at the IBM FHIR server, you're willing to, please feel free to post questions or ask issues, that raise issues there, and we'll take a look at them for you. So Q&A.
Thank you, Robin. I don't see any questions in Hoover. Let me ask those of you on site, do you have any questions? Okay, we have one question.
Thank you. Really appreciate that. That's novel, informative, and it's always good to see the new things or experimental things that are getting fully fleshed out. The one question I wasn't clear on, if sort of both that original method that you showed that was inefficient and then your new method, were those both synchronizing the entire history, all the versions? Because I sort of got the sense in the second go around you were just grabbing the most recent version of the instance. So are we replicating or just, yeah?
Sorry. Yes. Yeah. No. Absolutely. Yeah. It's
Robin, sorry for interrupting. If you could repeat the question for the sake of our virtual attendees, that will be great. Thank you.
Oh, if I can repeat the question? Yes, certainly. So the question was, with the different options that that I presented, the second option, was it specific to just replicating the most recent version of the resource, or the whole history of the resource? So it's the whole history of the resource. So the desire, or the intent here is to basically make the downstream system kind of a copy of the upstream system. Now, let me just make one particular point here. So the FHIR API itself, right, is not a good, it's not a perfect kind of sorry, the FHIR REST API, I should say, is not a great solution for kind of bit perfect copies of systems, right, for kind of replication in this way. And the reason is that it relates in particular to kind of failure scenarios where you may create a resource on the downstream system, then you get a network partition event where you don't actually get the response back. So the synchronizing system has no idea that it actually was successfully created on the downstream system. So so in that case, you can maybe it tried again, or it restarted, and then it may push that same resource. Now, depending on how the downstream FHIR server reacts to that, it may create a new version of that resource, which happens to be the same as the previous version. So now your versions kind of come out of sync, right? But that doesn't necessarily matter, really. So although your kind of downstream system isn't a bit perfect replica of your upstream system, the logical data, right, the health data that's represented by the resource is still accurate, right? You do still have the same data there, and you do still know which is the latest version. So I think that is okay in that respect. It's just that you need to be aware that if you're using this mechanism, your downstream system may have a slightly different version history, and certainly like the last updated times are going to be reflective of the time when we created the new resource in the new downstream system, rather than kind of copy the last updated time from the upstream system, if that makes sense.
It does, but it just sort of raised another question. So the last update, so for every version that goes into the downstream system, it's the last update date is reflecting the time it entered that system, not the original time it was in fact updated on the upstream. Is that correct?
Yeah, that's correct. If you're using the FHIR REST API, because that's what's defined with the FHIR spec. Yeah.
Okay. Yeah. Thank you.
There was one more question here.
Yeah, hi. My question is, you switched to that Kafka approach later. I was just wondering, why didn't you just go with like an event-driven? Is that not a pattern here, or was it like more for batch use cases? That this pattern was proposed.
Can you? So the question here is, why didn't we go with an event-driven approach?
Yeah, like using like a Devisium connector from your source and just connecting it directly.
So it was. I mean, there are multiple ways to do it, right? But because you're using the history API, you do have this single kind of touch point where you need to kind of stream the data, right? And so certainly when you're streaming, you mean, but so you're talking about some kind of reactive system where the results of the stream would then be just kind of distributed out, right? So you'd make the history call you'd get the bundle back, and then as you're processing the bundle.
Yeah, like typically that's how we do it these days, right? Like meaning that you do the change data capture from your relational database, streaming it into like a a streaming layer like Kafka, and from there you have a downstream connector, just like you did it now. So I was wondering, why do you have to actually pull using the history APIs when you already had a relational database and you could push it using the CDC?
Yeah, absolutely right. So okay, sorry, I wasn't sure what you were referring to. So yeah, with yeah, absolutely. So I did meant to mention change data capture and doing that at the at the database level. So that is absolutely a a viable approach for for doing this sort of thing. Now, where that might not work though is when your resource payload is not actually stored in the database. So you would still have to go out and pull that data, right? And so this is really just an exercise in this is mentioned in the spec as a way to do this. So we thought, let's take a look at this and see and see how it works. So it's really kind of an engineering exercise to see how how effective it would be. It is quite nice because it does decouple you, from the database itself, right? So the replicating system doesn't know really anything, or knows very little about the underlying system. It doesn't know that it happens to be a relational database, behind the scenes.
Thank you.
There is one question on FHIR. How did you generate data for integration testing? Synthesis data?
Yes. Yeah, we use Cynthia. We have a library of Cynthia data, and we store that in a bucket, and can pull that down wherever we need. We have some. In fact, there's a project on GitHub called FHIR Bucket that we actually use to pull data from either IBM's cloud object storage or some other bucket service like MinIO or whatever, S3 service, and it can basically pull that and then push it into a FHIR server en masse. So we use synthetic data for all of our testing.
Thank you. There's one question from here.
Thank you for your presentation. Learn some new techniques. I got a question, like if you are gonna query your history endpoint, does it add load, like query load to your original server? That's first one. And the second one is, have you thought about using export? Is that something, because export can usually implement it in a way that has a long running process, but reduce some burden on your original FHIR web server. Thank you.
Right, great questions. This is this is right up my alley because yeah, I actually implemented part of the bulk export backend implementation for the FHIR service, the IBM FHIR server. So yeah, the question is so one on query load, and then the second part of that was on export. So relation to query load, the actual query to do the history endpoint, certainly in our implementation, is very lightweight. So it's basically just translates to a database index range scan, which can be serviced in just a few logical reads, depending on how deep the index is, obviously. But so that is incredibly efficient, and you're talking millisecond, order of millisecond response times for that, and then being able to then go and read the resource, that's just a simple vread, right? So there's a few database logical reads for that, and then wherever you store your payload, whether that's a row in the so in fact, in the IBM FHIR server, we have a couple of options for where we store the payload. We can either store it in line in a CLOB, well, sorry, a LOB, large object. So basically in a database row, or we can also offload the payload as well, where you can store it in maybe S3 or something like that. And so by payload, I mean the kind of well, in our case, it's the JSON resource, right? It's a JSON serialized version of the resource. So from query load, it's pretty light. The history API is very, very efficient at pulling the data. And then the vReads, again, you should be able to support, on moderate hardware, tens of thousands of reads a second for that kind of thing. It's not too heavy. From an export perspective, so yeah, export's interesting, but it's a much more kind of, as you say, it's kind of it's an asynchronous process. You ask for so that kind of a range of data, you run the export, it sends it out to a system. So it's got its use cases, but I don't think in terms of maybe live synchronization, it's kind of the same thing. With this approach, you can basically have this running continuously, right? And then the polling will kind of just keep going 24/7, and it'll just, as new resources come in, it'll then just push them down to the target system. You don't have to run another export job or anything.
Any follow up on that? No, thank you. Any other questions? I don't see any questions from the virtual audience. I think we are done with the questions.
Well, thank you for the questions. Very good.
Okay. No more questions, right? Okay. Thank you so much, Robin. Thanks for the excellent presentation, and thanks everyone for attending, and thanks for the questions. Till we meet again. Bye, everyone.